Welcome to a new episode of our Ocean Networks Canada series, Surfacing Secrets, Explore the Ocean, Know the Planet. Today's theme is scientific discoveries, which sounds glamorous until you remember most discoveries begin with someone saying, that's weird. Scientific discovery isn't usually a lightning bolt moment. It's more like a slow burn mystery with spreadsheets. And occasionally, hydrophones, landslides, and a solar flare messing up with your instruments just to keep things interesting. In this episode, we are following 3 different paths into ocean science and one common obsession: staying with the data long enough to catch the ocean in the act. You'll hear from Richard Dewey, one of the original architects behind ONC Observatory System.
Richard Dewey, just retired, but I was the prior science director with Ocean Networks Canada.
Kohen Bauer, whose work sits at the intersection of ocean data, tools, and models.
My name's Kohen Bauer, and I currently serve as the Ocean Networks Canada Director of Science.
And Gwyn Lintern, one of ONC's early partners working with Natural Resources Canada, whose research takes us from big ideas to very real risks on the seafloor.
I'm Gwyn Lintern. I'm a research scientist at Natural Resources Canada, and specifically a part of that called the Geological Survey of Canada Marine Section.
This is Scientific Discoveries. When we talk about scientific discoveries, we often imagine breakthroughs, moments, headlines. But most discoveries don't start with an answer. They start much earlier with curiosity, doubt, and a decision to follow a question instead of a plan. Let's start here. Take Gwyn. When you hear paleontology, you picture Indiana Jones, right? Dust, fossils, adventure. It turns out it's not always that cool.
So mine starts really in high school. I took the earth science class, and I loved it. And it got me into all sorts of interest in outer space and planets and astronauts whenever they came to town, giving talks and that sort of thing. And I got very inspired to do paleontology, and then ended up going to Australia, working on paleontology there in a museum. And the dream of paleontology kind of got worn thin by seeing how much these paleontologists were struggling to make a living. And, and I was like, wow, okay, it's not quite the dream you might think of, the Hollywood dream to be a paleontologist. Cooped up in their labs looking through microscopes and things and struggling to find any funds and that sort of thing. So I ended up doing a further degree in the University of Wales in ocean science.
And then comes the moment everyone finds confusing, walking away from Nobel Prize conversations for the good life of British Columbia.
At the time, I'd been at Oxford for 5 or 6 years. And it was its own lifestyle. It was an amazing place. I was running a society there, a Canadian society. And so basically I could invite any Canadian I wanted to come and give a talk at Oxford. So I ended up meeting some really interesting Canadian leaders and things. Nobel Prize winners, astronauts, leaders of banks, generals, this kind of thing, authors. But I also missed kind of the West Coast lifestyle, fishing and that sort of thing. I'm a big fisherman. And so one night I sat there at Oxford and I kind of turned this into a thing. I said, all this high table dining and all these balls and all this stuff is great, but I just want a boat and a barbecue. And that was kind of my mantra for coming back to the West Coast.
For Richard, discovery didn't come from switching fields. It came from realizing the ocean had already been shaping everything.
I grew up in Victoria, and my family sailed on the Salish Sea all the time. We went cruising in the summertime. We raced in the winter. This is one of the most beautiful places on the planet. And so I sort of grew up very familiar with being on the water. My father was a professor at the University of Victoria. I did my undergraduate in physics at the University of Victoria. I wanted to go to grad school. I liked research, but I didn't know what I wanted to do. I didn't really know how to apply my physics. And I had a professor who was an oceanographer, and he said to me, what about oceanography? And all of a sudden, all the lights went green, right? Live on the ocean, apply physics. It's relatable. It's important. Just doing oceanography is so rewarding.
And then there's Kohen. Same curiosity, but his story starts with a very Canadian kind of assist.
I started my undergrad studies at Queen's in Ontario. I'm originally from Ontario. That was in geology. So that's when I became interested in the Earth system more broadly, I would say. And then towards the end of my degree, I really got interested in marine geology, right? So these are processes taking place in the ocean. So you don't learn anything about geology, or at least I didn't, about the Earth system. Right, in high school, you get chemistry, physics, biology. And then I got to university and I took an elective by chance. I went to school, I thought I was going to be a physicist. And in my first year at Queen's, I took an elective course called Natural Hazards. And this was all about volcanoes, earthquakes, you name it, right? Natural hazards. It's obvious what the course was about. And I had this professor named John Haynes, really enigmatic guy, really special, charismatic, bizarre person, but totally inspired me. He still taught on transparencies. So you had to go to his class. This was a class of like 300 students, first year students, and he would write all his notes on overhead transparencies still. He would point at them with a hockey stick. So he walked around the room with his hockey stick and his long gray hair, and he would, it was amazing. He was like totally changed my life, actually. I was totally hooked and I never looked back, actually.
3 people, 3 ways into ocean science. No one here set out to make discoveries. They followed questions and didn't stop when things got complicated. And that's where discovery actually begins. Up to now, we've talked about curiosity. But curiosity alone doesn't make discoveries. Discovery needs something much less glamorous: time. And that's where Ocean Networks Canada comes in. Richard was there when the idea still sounded slightly unreasonable.
So you've got to realize in 1991, the World Wide Web didn't exist yet. There was an internet. There were military and university networks, like DARPANet. And I remember even in the 80s having, I was at UBC and doing my research at the Institute of Ocean Sciences in Sydney. And I would connect from Sydney to a computer at UBC. And this was fascinating stuff. I really thought, oh my God, here I am on a terminal connecting to a computer somewhere else. But the World Wide Web didn't exist until the mid-1990s. But by the late 1990s, we thought, well, let's bring the oceanography community into this new world of wiring the world. The world was now wired, but the ocean wasn't. So we needed to bring the ocean to the internet and to the World Wide Web. We could install a system and have live data going to anyone with an internet connection. And so this was quite revolutionary. When I started, to be an oceanographer, you needed to live on the coast. You needed maybe to have access to ships and very expensive resources. Well, Ocean Networks Canada breaks down that barrier. We have researchers that can be completely landlocked. They don't have to access large, expensive ships. They don't have to become experts in these data systems or the instruments. They can come and they can explore the archive from anywhere with an internet connection.
So now anyone, anywhere can be an oceanographer, which means discovery isn't about finding a needle in a haystack anymore. It's more about realizing you're standing in a warehouse of needles.
We have petabytes of data over a decade, right? And the whole point is that to chase down these observations and turn them into discovery, that's what makes it fun, right? You never know what you're going to find. When we have a hypothesis or a scientific question, it's important to follow up on that. And then really, like, the data that we collect is not for ONC, it's for everybody else. We want everybody else to make use of this data and to come up and create knowledge. And so really then it's engaging with the scientific community to ask questions and interpret that wealth of data.
And sometimes creating knowledge isn't about finding what's broken. It's about realizing when a system is actually doing what it's supposed to do, which is oddly reassuring, especially in an era where most environmental stories don't come with good news.
And the Salish Sea, in particular, Strait of Georgia as an example, is remarkably healthy because of the oceanographic conditions driven by tides and the river flow. And we get a good exchange with the ocean because of the Pacific Ocean, because of the estuarine circulation from the Fraser. We get vigorous mixing because of the tides. And that combination results in a really quite healthy ecosystem for phytoplankton, herring, salmon, all the way up to marine mammals and whales.
The ONC facility evolve and continue to contribute the observations and tools needed to ensure that the Salish Sea remains a healthy ecosystem.
And we're monitoring that health in real time.
Same ocean, same physics, but very different choices upstream. Apparently, ecosystems have opinions about policy choices, especially the ones made far from the shoreline.
Well, it is kind of interesting. It is interesting. I mean, the Puget Sound is I won't say less healthy, but they've got issues that we don't have. And I don't want to bring that up too much, but for example, they have a lot of agricultural fertilizer runoff in the Puget Sound. It results in over-fertilizing the ocean. And when you over-fertilize, you get unnatural blooms, if you like, biological blooms that then sink down and you get hypoxia. It turns out on the Canadian side of the border, we have very clean runoff. The Fraser River and all of our rivers are remarkably clean, very low in pollutants, very low in fertilizer. And the whole system works with the tides to result in a very healthy ecosystem.
When you have this wealth of data, how do you operationalize it to learn something or to, for lack of a better way of saying it, manage the Salish Sea so that, again, it remains, it can be stewarded and protected. And this concept of a digital twin came up. And so this is, a frontier sort of space in the big data and modeling world. And the digital twin is a model of a natural environment, or it could be a model of many models. And so what you need to make an accurate model is robust data, observations that tell you how the ocean environment is behaving and how these processes are interacting.
And once you're watching continuously, something unexpected happens. You start noticing things you weren't looking for. And that's the thing about discovery. You have to go looking for the weird. Okay, now let me tell you about some of these wait, what moments. Because once you start looking for the weird, you don't get answers right away. You get raised eyebrows. And sometimes the ocean doesn't whisper, it makes headlines. And that's exactly what happened with the blob.
Yeah, that was a major event. And the blob we're talking about, the marine heat wave that started in 2013 to 14, was really far out to sea. It was at the surface layer of the ocean in the Gulf of Alaska. The entire Northeast Pacific was very, very warm that spring of 2014. And it wasn't until about a year later that water started coming near shore that our sensors picked it up. And so it was kind of exciting to see as this blob evolved from an offshore event to a coastal phenomenon. It raised the temperature of the coastal waters, in particular along Vancouver Island and into the Salish Sea, by about 2 degrees for 2 or 3 years. And it stuck around for a very long time. And again, this was not at all anticipated. We're familiar with marine heat waves. They seem to be becoming more frequent with climate change, but their persistence that it lasted offshore for over a year and then inshore for another 2 to 3 years. So the heat wave that was called the blob had such a large temporal and physical footprint. It was really quite remarkable. It's probably the largest marine heat wave ever recorded, and our data was contributing to its understanding when it came ashore. And it lasted for 3 years. It elevated the temperatures in the Salish Sea. We had, in fact, there's sort of an annual cycle. This is one of the things that the observatory picks up. It picks up all the variations, including annual cycles. And when the blob was along in the Salish Sea, The coldest temperatures we were seeing those 2 years, like the 2016 and 2017, the coldest temperatures were warmer than the warmest temperatures in some prior years. So the whole system, it shifted up by 2 or 3 degrees, which was not anticipated. And the data, this long record really helped us put it into context.
And if you think that was weird, wait until space starts messing up with your instruments.
These little gold nuggets in the mine of data that we're collecting, they're probably limitless, right?
Weird number 2, when space messes with the ocean. This one, no one saw it coming.
Like one example I can give you that happened recently was that a couple months ago, there was a very strong solar flare. This is an example of a data specialist at ONC who's the person that recognized this. His name's Alex. So he was monitoring a bunch of streams of sensor data, and he recognized that there was something weird happening in this data, and all of this, and in particular in the compasses. So there's a particular instrument that we have in many different locations on our network called an ADCP, and as part of this instrument, there's a compass sensor as part of it, and the compass readings were behaving strangely all at the same time, and so then Alex contacted a few other people at ONC and is like, what could be going on here? His initial hypothesis that it could have been an earthquake. But then in reading more into it, it just happened to coincide with a major geomagnetic storm, like a solar flare event, right? And that this type of electromagnetism in the atmosphere was essentially screwing up the compasses across the ONC network. It's really that cool, right? So something that's happening, it's like an astronomical phenomenon, but we're recording it in the deepest parts of the ocean. So it's pretty neat. That we don't really quite understand the implications of that yet. Right now, that just still stands as like a very cool observation. Why that's important and how we can learn from that, we're still working that out, and that's part of the process, right?
You think you're studying the ocean, and then suddenly the space shows up. That's discovery. And once you've seen one weird signal, you start wondering what else you've been missing. That's when listening starts to matter. Quick reality check. Underwater, vision is useless pretty fast. Sound is what actually travels. And if you want to catch the weird, you have to listen.
We have cameras that can see within a meter or two of the observatory, but we can't see very far away from the actual node and the actual instrument platforms unless we use acoustics to probe. And we can probe with acoustics great distances.
Hydrophones are basically a mystery box. You don't choose what you hear. You just hit record and brace yourself.
And it's a very dynamic environment, and sound propagates a long way. So we're hearing things from maybe kilometers away, and it's very, I wouldn't say it's noisy, but there's sound almost all the time from all these different processes.
Of course, some cool observations are the one you were looking for.
Occasionally, we get the orca whale vocalization. So that's pretty exciting, like you're talking about, when we're hearing marine mammals. Some dolphins vocalize up at 50 kilohertz, far above what we can hear. So we sample acoustics at like 128 kilohertz. So you're making a 32-bit sample 250,000 times a second, continuously 24/7. So right away, a hydrophone sitting in the ocean is collecting terabytes of data on an annual basis. And we've got dozens of hydrophones. So it's hundreds of terabytes.
That's biology doing its thing, right? It's cool, but not the weirdest part. Then you start hearing things that definitely don't belong underwater.
We had the first hydrophone was in Sandwich Inlet, and turns out it's near an airport, and we could hear planes flying overhead, and we could, in particular, if there was a seaplane taking off or landing, you could hear the seaplane. And in the coastal waters, like the Strait of Georgia, we sort of have the background din of almost continuous ferry traffic and freighter traffic.
Turns out the ocean is a very honest recorder. It hears everything, including us. Okay, quick reset. Not all weird sounds are animals. Some of them are the planet adjusting itself.
The other hydrophone that I think was really quite fun to listen to was one we installed in Cambridge Bay up in the Arctic, in the Canadian Arctic. And at this site, it gets frozen over in the winter. And we anticipated that we might hear some ice cracking, and that was, sort of really scary to hear. You wonder, because it's a sort of a real violent cracking sound as the ice cracks. But then also, as the ice got thicker, the community started to drive on the ice, both in cars and in snowmobiles. And so the pervasive sound later in the winter was all the community driving on top of the ice in their snowmobiles and cars. So we had not anticipated that, and that gave us sort of a window into the community going out on the ice and using the ice as a highway. Then offshore, we have hydrophones at places like the Endeavour Ridge, where there's earthquakes and other things happening. There's vents, hot vents, black smokers, and you can actually hear with sort of a venting sound, and you can hear earthquakes. We often have earthquake sensors that are really feeling the movement of the earth, but earthquakes also generate sound. And it turns out at these places, this ridge in particular, is very active, and there are hundreds of earthquakes a year. And so our hydrophones are picking up earthquake sounds, grumbling and venting on a continuous basis.
This is how discovery usually happen. We already watched space mess with our compasses, so the obvious next step was to try something even riskier. Put a lot of very expensive gear on a moving seafloor and see what happens. That was Gwen's idea.
The composition of marine sediments, the stuff that is accumulating on the seafloor, tells you a lot about what's going on in the ocean environment.
Yeah, and sometimes they also mess up with your entire experiment.
Wanted to look at all the delta processes that were taking place on the slope of the Fraser Delta, an important river coming out of Vancouver near the airport.
So the Fraser River dumps all this water, but it comes down with a huge amount of sediment loading. And all this sediment is building up the delta. The whole Fraser River Delta, Richmond Delta, built on this sediment that's come down the river. And it continues to bring sediments down on an annual basis. So the freshet happens when the snow melts. All that sediment and water is coming out in May and June. And it deposits a huge amount of sediment on the slope as the river spills out into the Strait of Georgia.
There's some areas of the delta that look like at the bottom of the slope look like kind of piles of sediment as if it had failed. These type of underwater avalanches, let's call them, but they're actually called turbidity currents. They're a mass of sediment and water that flow hundreds of kilometers off coastlines and can damage cables and pipelines and that sort of thing. They were known in the world, but they were hardly measured at all.
And Gwyn wanted to put a platform. So he basically came to Verena and I and said, we have this idea. We want to put a platform right as close to the mouth of the Fraser River as we can. We want it cabled because what we want to do is see all this process that's happening.
We specifically wanted to be looking at submarine landslides. And these are events that occur just, they could take a few seconds and they may occur just every few months or every years. And so that was the power of a live observatory, is that we could monitor for years and capture these events that take just seconds. And nothing else could have allowed us to do that sort of work. And there were sort of two main platforms. One was a delta platform measuring sort of oceanographic properties, and the second was one that would penetrate into the seabed to measure slope properties, slope stability properties, and that sort of thing.
Gwyn told us, there'd be maybe a foot of sedimentation each year accumulating. And so we put a platform on the delta slope, and we went out to service it, and it was completely buried. It was buried under about 1.5 meters of sediment. And we couldn't bring the platform back. We eventually did get it out of the sediment, but And his response was, oh, well, yeah, during the freshet, it can dump as much as 2 meters of sediment on. And over the year, it washes away. And we're like, oh, well, that was a bit of information that would have been really helpful for us in designing the platform.
The sort of rumor is that that during an earthquake, this slope could fail and cause a tsunami or big damage to things on the slope. That's the sort of rumor.
And you get a landslide. It builds up. It's not consolidated, and the whole slope slips away, slides down, and slumps away.
And so the idea of this platform was to try to get some answers on that. And so it was built as a platform that would measure things like ground shaking, sediment movements, and the different forcing factors that could cause a landslide.
And so we listened to this and we said, what do you mean? You want to put instruments there, but you want to record for a few years, but hopefully they all get swept away in an avalanche? And he's like, yes, that would be fantastic.
And so we now had this platform that was basically in the path of these.
The platform had over a dozen instruments, all sort of measuring very high speed, up, down, looking around. And it got hit by a landslide. It was still cabled, so the instruments were still working. And so in the acoustics, we see this sediment increasing around the platform. And then the platform starts to move, and then it actually starts to tumble. And it turned over 2 or 3 times before the cable parted. And some of the instruments were sampling fast enough that they captured this as the instrument is tumbling down the slope.
And then, of course, we lose the signal.
And then the cable parted and we lost all the data.
And all of the engineers and the managers and all the people are concerned. What's happened? And so they're looking into what's happened. How are we going to get this back?
And it was a bit of a shock to us because here we were investing all this effort and money. And one of the things we tried to do is make sure these instruments aren't lost and don't get carried away. And they stay there and say, and this whole experiment was an attempt to say, no, we want a disaster to happen. And sure enough, it did several times.
As scientists, we're sort of looking at each other thinking, could this be it? And so we spent a few days going through all of the last few seconds of data. And eventually you just, I think that the main one, it's all tangled because the instrument was tumbling. But once we saw that, the instrument had tumbled, you could see that clearly in the pressure data that the instrument was tumbling down the slope. And once we put it all together, you sort of, I guess, you ask what it's like, you kind of, at that point, you sort of lean back in your chair and clap your hands together and say, this is it. This is what we had. We had some idea that this could occur on the Fraser Delta. We had seen sand waves before that indicate that sediment's moving in a single direction, just like in sand dunes on land. And we'd sort of seen evidence that these could occur. And so it's kind of a big moment in your career to be working towards something and then be able to just say, that is it. We have irrefutable proof.
So this became a very risky project for us, experiment, because we sort of were building a system that the scientists were aware it might get swept away in a landslide at some point in the future. Hopefully they would collect a lot of data and see it.
Now that we know that they occur here, we've actually started to be able to predict them based on tides and how the rivers, how much sediment is coming out of the river and that sort of thing. And we can sort of go from almost having no measurements in the world to now practically predicting them just in that 10 years of research on the network.
Gwyn foreshadowed this. He basically said, I want to collect a couple of years of data, and then hopefully it gets hit by a landslide. And sure enough, that's what happened. And we as the sort of the operators of the observatory said, well, the experiment's done. He said, no, I want to go back and do it again.
So yeah, the experiment didn't survive, the equipment didn't survive, but the idea did. Because this wasn't about hoping nothing would happen. It was about being there when it did. And that's how a terrible plan turned into a discovery that's actually useful for science and for safety. Okay, that landslide story wasn't just an anecdote. It's a perfect example of how discoveries happen, not by luck, but because the system was built to catch them. So let's zoom out for a second, because this episode isn't just about one experiment that went sideways. It's about how Ocean Networks Canada creates the conditions for discoveries to happen again and again.
The ONC network, by definition, is very data rich, right? So we are making measurements every second across a diversity of ocean environments. And so it can be a challenge to really keep up to date and monitor all those streams that are happening in real time.
And that's not a bonus, that's the starting point.
Is to just ensure that we have the right observations in the right places, and those observations and that data is of high quality.
We've got core sensors that have been out there the whole time, and they are sort of painting the canvas of the ocean. They're showing us the background, persistent process that happen on tides every day, seasonal variations every year. And onto this canvas now, researchers can come to us. We've got this history of how the ocean is responding in this area, and then they can plan an experiment with a lot of knowledge about what they might expect, and then they can fine-tune the experiment to really look at things that you wouldn't have been able to do if you came and you didn't know what the environment you were going into. So we've got the Ocean Networks Canada provides this canvas onto which you can design really specialized and very rewarding experiments.
And someone had to build a canvas before anyone could start painting.
Connecting with the community to ensure that we have the right tools in the right places, right? At the Fraser River Delta, in the urban seaways of the Vancouver ports, for example, in Saanich Inlet, right? Where should these tools be and what should they be comprised of so that we can continue to provide the data well into the future that people in the Salish Sea will rely on?
Because putting instruments somewhere is easy. Putting them in the right place, that's the whole game.
I think the biggest impact or the most amazing thing working with Ocean Networks Canada was the fact that we were building something with the science community. And it's a big network of researchers. And we were enabling new things that they wanted to do. And it was our job to go away, take their ideas, build a system, install it in the ocean, get it working, and then work with them to get scientific discoveries. And this network of researchers, we're talking about hundreds of researchers doing many, many different things. And I think it continues to be one of the most exciting aspects of Ocean Networks Canada. We're making such a big difference to so many researchers across all range of marine science. So I think that was unanticipated and most rewarding.
And I think it just takes a certain sense of creativity and thinking outside the box. I mean, you never know. I'm convinced that there's many, many, many discoveries like the ones that we've been talking about that already exist in the data in archive that we have on the ONC network. And so it's just going to take that spark of inspiration or the right person asking the right question to say, hey, what if we looked at that? And what do you think that means? And that's what scientific discovery is all about. And that's why working at ONC is such a cool and special job.
What Kohen is describing didn't happen overnight. In the early days, ONC was focused on building the capacity to observe, installing infrastructure, learning how to watch the ocean continuously, and responding to the questions that emerge along the way. Fast forward a few decades, and that long-term vision became something robust, reliable, widely used, the kind of foundation entire federal departments can now rely on.
So I've basically supported ONC since the day I arrived here in Arcan. We have an agreement in place where we share equipment and ship time and personnel. And ONC has grown from really needing that support to kind of then almost supporting me more in my science. And so it's been amazing to see it go from kind of 4 people to a team of probably 100.
So when you hear scientific discoveries, don't picture a single aha moment. Picture a system designed to stay curious, long enough for the ocean to surprise us, and stable enough to make those surprises useful.
It feels pretty cool to be involved in really leading edge science like that.
And that's where we'll leave it. A big thank you to Gwen, Kohen, and Richard for taking us inside what scientific discovery really looks like. Not the polished version, but the real one. Long-term, curious, sometimes messy, and often surprising. This podcast is produced by Balad'EAU with the generous support of Ocean Networks Canada. ONC is one of Canada's major research facilities and is an initiative of the University of Victoria. It is primarily funded by Canada Foundation for Innovation and by Fisheries and Oceans Canada. Thank you as well to Tommy Goupil for editing and production, and to Andrew Lowen of the How to Protect the Ocean podcast. For this series, each episode comes in 2 versions: the full interview with Andrew and this narrative episode, more storytelling style, here on Balad'EAU. If you want to dig deeper, you'll find tons of great contents on Ocean Networks Canada's website and social media. And if you're curious to hear more from Richard, he also runs a really great YouTube channel where he shares ocean science in a very accessible way. It's in the show notes of this episode. I'm your host, Lyne Morissette. Thank you for listening, and keep an eye on the data. It's usually trying to tell us something.